Today we're talking about radicals and rational exponents. In general, for an integer n greater than 1, if b to the n equals a, then b is an nth root of a. An nth root of a is written as, and you can see here we have the radical sign with the little n inside this kind of V shape with a underneath the radical. This is called a radical. And n is the index of the radical. So the n is the thing that's sitting right in here. Notice it's not out in front. We're not multiplying it by like the square root of a. This index is sitting right there in the radical. So then what I want you to notice here is we have a couple of things. Number one, the nth root of a. If the n is odd, there's only going to be one real nth root. If the n is even and a is a greater than 0, there'll be two answers, okay, the positive and the negative. If n is even and a is equal to 0, there's only one nth root, and that would be 0. If n is even and a is less than 0, there will be no solutions or no real nth roots. Okay? So nth roots may be real numbers like we're talking about, or possibly imaginary numbers, which you'll study in later courses through the high school. So let's just start looking through some of the examples. So finding nth roots. So find the indicated real nth root of a. So to write this out, we know that this should look like there's the index and there's the base. Okay, so to write this first, we want to make sure we understand we're working for the third root of negative 27. What that basically means is I need to find some number times itself 3 times, because the index is a 3. So because that's a 3, I need something times itself 3 times that will give me negative 27. So hopefully we can see that number. Negative 3 times negative 3 is positive 9, times negative 3 is negative 27. So negative 3 is the answer. It can also be positive, because positive 3 times positive 3 is 9, times positive 3 is 27. Can only be one answer here. Okay, looking at the second one. So then, again, the a goes underneath, and then the index, the nth root, is 4. So now we have to think, what is something times itself 4 times? Well, hopefully we can see 2 times 2 is 4, times 2 is 8, times 2 is 16. But thinking about that, isn't there another solution? Negative 2 times negative 2 is positive 4, times negative 2 is negative 8, times negative 2 is 16 also. So this one has 2 solutions, both positive and negative. And again, as one of the kind of rules we just saw up above, if you have something here that's greater than 0 with an even number, it'll have 2 answers. This one happens to be a nice easy one, perfect 2. But if it's positive and has an even number of n's in our index, we should have a positive and negative answer. All right, so evaluating the next ones. So now we're going to look at one of these. So we have the third root of negative 8. So again, you have to think out, we need 3 things that if I multiply together, negative 2, negative 2, negative 2. So negative 2 is my answer here. So next we want to look at the negative third root of 8. So this one's a little bit trickier. You just got to think out what would be the next thing. So we want to look at the third root of 8, looking for 3 things to give me positive 8. So again, this one would be 2 times 2 times 2. So we would have negative on the outside still a 2 from the inside. We also get a negative 2 as my answer. Just notice that A, we had the negative 2 as kind of like the root. The root is actually a 2 for B, not a negative 2. But then the negative on the outside means we wanted the negative third root. Okay? So then we see this fractional exponent thing. And this kind of goes back up to the above ones that we're talking about, these fraction exponents. So for the fraction exponent, what we're going to do is the base is the 16. Then we put the radical sign around it. And the 1/4 means this is the 4th root of 16. All right? So we're not going to show this in this case, but really, where does that 1 go? The 1 is sitting right in there. So that numerator of 1 would go with the base on the underneath radicand sign. The 4th root goes into that. And again, notice I don't have that 4 out in front of this whole thing. It's tucked into that little valley there. So then what I'm looking for is the 4th root means I need 4 things that multiply together to give me a 16. So on a previous example, this would be one that we consider the positive and the negative. But again, remember the notation when we did our square roots. When you have just the single radical with nothing in front with the plus or minus, that normally means we just want to have the positive. So we would be looking at 2 times 2 times 2 times 2. So the answer to this would be the 4th root of 16. In this situation, with the radical sign all the way around it, and this fractional exponent would be just 2. The difference being up here, when you just generically say, what is the 4th root of 16, then you're kind of considering both. This notation here says, really, we just want the positive. On the next one, so something similar, we're looking for the 4th root of negative 16. So here is one that we want to kind of start this out. Negative 16 goes under, because remember, the exponent goes to the very first thing it hits, which would be the parentheses. So the radicand has to be the negative 16. So the question is, what number times itself 4 times would produce a negative number? Well, nothing. Because if it was a negative answer, the 4 negatives become positive. If it was a positive answer, all 4 times themselves would still be positive. So in this situation, we're going to write no real numbers. Okay, so again, you'll talk about imaginary numbers when you get to the high school levels, but for now, we haven't studied those. You would just say no real numbers. So rational exponents. So what are we going to do if we have situations where now we don't just have a 1 in the numerator? Well, if you remember back to the power of a power, we're going to take something like this, 27 to the 2/3 power. We can break it down to be 27 to the 1/3 raised to the 2nd power. And that would give us the same thing as 2/3. Remember, power of a power, in the mad spam rules, you multiplied those two. So we're going to use that information to create this, because we know 27 to the 1/3 power is the cube root or third root of 27, and then we would square that answer. So let's look at a couple examples. So this first example, 16 to the 3/4. So I'm going to write this as to the 1/4 raised to the 3rd. Just kind of breaking it apart, looking at that power of a power. Well, if I do the 16 to the 1/4 power, it would look like that. we just saw in a previous example, the fourth root of positive 16 would be 2. And then 2 to the third power, 2 times 2 times 2 is 8. On the next one, if I take 27, and again, if I break it down, and I make it to the 1/3 raised to the 4th, that is going to be the cube root of 27 raised to the 4th. The cube root of 27 is 3, because 3 times 3 times 3 is 27. And then 3 to the 4th is 81. Okay, so it's just important that we remember, and then obviously being able to go backwards too. Remember, the numerator would stay with the outside afterwards, and the part that goes in for the index or the root number, think of the 3 in the denominator as the root of a tree. It's in the bottom of the tree. The root would go into that V out in the front. So then lastly, we have this one here, just a real life problem. So we're talking about the radius of a sphere that's given by a equation r equals 3v over 4 pi to the 1/3 power. V is the volume of the sphere. Find the radius of the beach ball to the nearest foot. Now, in a previous example, we talked about using just the pi symbol. But here they're saying use 3.14, so we're going to use 3.14. And we're going to eventually be searching for the radius. So let's just start plugging in what we have. So here is the formula. We have 3. The volume we are given is 113 over 4, 3.14. And then we are doing the 1/3 power. So we're just plugging in first what we know. So then we would have radius is 339 divided by 12.56. And we're going to hold that there for now. And then we're going to get radius, and this, it's going to be approximately 26.9. So I'm going to round it, partly because I know this is a perfect cube. So then my radius is going to be the cube root. Remember, the root, the denominator goes into the index. And then that's going to tell me that the radius, 3 times 3 times 3, to the nearest foot. So we're going to say the radius is 3 feet. Okay? Just plugging in the formula and following the formula. So remember, we just kind of worked through the inside those parentheses, made sure we did that first. Once we got it all the way boiled down, then we could take care of the things outside of it. And then our last example. So to calculate the annual inflation rate R in decimal form, so we want to keep that in mind, of an item that increases in value from P to F over a period of N years, we can use this formula. Find the annual inflation rate to the nearest tenth, and it's important that we see that, of a percent of a house that increases in value from 200,000 to 35,000 over a period of 5 years. So we would be using P. P would be our 200,000. F would be our 235,000. Over 5 years, N is our years. So that would be just looking at our information. So then we just start plugging in the formula. So we have R equals, notice that the F is going to go up in the numerator. And we're going to do 1/5 as the power, and then we subtract 1. So then we would have 1.175 5 to the 1/5 minus 1. And now at this point, we're definitely using a calculator. And when I use my calculator, I am going to get 1.0327, and I'm just going to stop it there, minus 1. And when I subtract, I get 0.0327. But then remember, we want to have the inflation rate, which is a decimal form. And we want to go to the nearest tenth of a percent. So remember, to go from a decimal to a percent, we would move this over 2 places. We want to know the tenths of a percent. So 3.3% would be the annual inflation rate that we saw if we went from the 200,000 to the $235,000 difference. So it's just more a matter of just understanding how these exponents are working, these fractional exponents, and how to write them as in radical form as well as the rational or fraction exponent form. If you have any kind of questions, please feel free to ask when I see you in class this week.